we solve a couple of exercises and on new material. I want to start with exercises about range. So we haven't done any exercises about range or function. We talked about domain, but not about the range. We did have some exercises in your skills module, and the word range will appear in the midterm. So I want to remind you what it is, just in case you probably know. Range. If you recall, the domain of a function was the set of all possible inputs to the function. For example, if your function is something like 1 over x, then you can take any number which is not 0 and plug it into this function. Compute what is 1 over x. And the set of all numbers except for the number 0 was called the domain. The range of a function is not about the inputs, it's about the outputs. So the range of a function is the set, or in other words, the collection of all possible outputs of the function. So if you recall the most strange example of a function, we had a function which took a student and the output was the share of which the student was sitting. So the domain of such a function would have been students in the class. The output, the range of this function would have been all seats which are occupied by at least one student. So, of course, we are not going to talk about such strange functions. We are going to talk about numerical functions, so like 1 over x or x squared. So let's look at some examples. Let's say my function is a linear function. The simplest possible example of function, and we have the linear function. What would be the, let's start with domain. What kind of numbers can you plug into the function? Yeah. All real numbers. So domain, we have this notation for all real numbers, or we can say all numbers. What is the range? What are the possible outputs? Okay, so this question is not as easy, but it's also pretty easy. So what number can be written as 3 times some number plus 5? That's the question. What number can be obtained as 3 times something plus 5? And the answer is, yeah, all real numbers. Yes, you can write any number as 3 times something plus 5. Just take this output, subtract 5, divide by 3, and you'll get the input that will give you the exact output. The range is once again with all real numbers. And there are two possible explanations. One explanation was what you just said in words. Explanations. One, to get just any number y in the form 3x plus 5, take x, which will be y minus 5, divided by 3. So if you want to get any output y, you can find them corresponding input. Just take x to be y minus 5 over 3, multiply it by 3, you get y minus 5, add 5, you get y. And it works for any y. Another explanation, which is maybe even better for our purposes, would be a graphical explanation. We already discussed graphs of such function. So another explanation the graph of this function, what is it? Well, it's a linear function. We know what a graph looks like. It's a line. Line with slope 3, y-intercept 5. So it's such a line. This will be 5. If you make one step to the right, you'll make 3 steps up. Now, how to see the range of this function? So, the range is the set of all possible outputs, which means all possible y values for the function. What kind of y values can you get? Well, any y value. For any y, there is some x which gives you this y. This line goes as high as you want and as low as you want. So, range is all possible y values. In this case, all values, all numbers. So, because we talked quite a bit about graphs of functions, transformations of graphs, maybe this method is actually preferable. Just look at the function, try to figure out what the graph looks like, and then what are the possible y values. For more complicated functions, maybe for which the graph is complicated, but this method works, well, sometimes you can also use this method. So, let's have more complicated examples. And before I go to more complicated ones, any questions about the simple one? Yeah?
So for exclamation one, the way to figure out that it's for all possible values, you figure out if that function is an undefined conditional point, and that's the first part, was it?
This one?
Yeah.
Yes. So this function is defined for every y. For every y, I can find the corresponding x, such that if I plug in this x into here, I'll get y. So that's why I can take any y. Other questions? Yeah?
When we're entering the exam, do you want us to use words, or should we use the notation that we use online?
Use whatever. You can use, if you want to express that the domain is, say, all numbers, you can say R, which is the set of all real numbers, or you can say all numbers, or you can say the interval from minus infinity to infinity, excluding the infinities, whatever you prefer.
Does that go for groups as well?
That you can use whatever notation, or you can replace notation with words, yes. I mean, we are not going to punish you for writing instead of the number 3, the word 3, it's fine. And we want to understand it, to understand the essence. We'll have more complicated examples. So other questions about this example? Okay, so let's have something more complicated, or much more complicated. F of x is x squared. So domain is, once again, all numbers. So let me use this notation if you want. So domain is all numbers. What is the range of this function? What kind of numbers can you get as something squared? Yes. So as a square of a number, you can get any number which is positive. And two explanations for this. So range is all numbers such that x is positive, or if you want, you can say all numbers from 0 to infinity, whatever notation you prefer. Why is that? Well, explanation. Once again, you can argue in two different ways. Y is equal to x squared has a solution, well, for x which is square root of y, and can take square root only out of positive numbers, which exists for y which is positive. That's one explanation. Another explanation, which will be parallel to this one, think about the graph of this function. We have this graph, a parabola like this, and what are the possible y values? Well, if you take y value above the x-axis, you will find the corresponding x. If you take y below the x-axis, well, no corresponding x. So only y's above the x-axis. So that's the range. Yes, and actually, when I was talking about the range, maybe it's better to denote the unknown variable as y, because that's the possible outputs, not the possible inputs. So I change this. It should be y and r, such that y is positive. Okay, so now let's go to something even more interesting. F of x is x minus 3 squared plus 5. So for such a function, well, the domain is once again all real numbers. You can plug in whatever. The range, what's the range is going to be? Well, let me go straight to the graph of this function, because it would be a good exercise also to recall how transformations and graphs work. So this function is basically squaring, except you don't square x, you square x minus 3. And you don't stop there, you take the answer and add 5. So it's basically the same function, but after some transformations. So let's sketch the graph. First of all, the graph of x squared we just decided was a parabola like this. Next transformation would be graph of x minus 3 squared. How would that look like? Yeah?
Move over to the right.
To the right, yes. So I move this graph to the right by 3 units. One way to check whether it's to the right or to the left would be, well, here I have a point which is very easy to compute. I plug in 0, the output is 0. What number should I plug into this function to get 0? Well, 3. So this point is to the right, so it must be the slope point section to the right. And finally, x minus 3 squared plus 5 was the, how can I get the graph of this function out of the graph of this function? Yes, so lift it by 5 units. Shifted by 5 units up. Because I'm taking the same output, but then adding 5. So the value over 3 is going to be 5, and then it's going to be a parabola. So what is the output? What is the range? What are all possible outputs? All possible y values? 5 and up, yes. So every value from 5 upwards can be obtained. Range all real numbers which are at least 5. Explanations about this. This actually exercise very similar to one of the exercises which appeared last year in the midterm. So that's approximately the level of difficulty of exercises that you should expect. So let's say this exercise combines two notions. One notion is the range of a function, the other one is transformations of a graph. So that's very typical of our questions. Yeah.
So when I solve it, like explanation one method, you have the square root of 5 minus 5, but
Yes.
then you have the plus 3. What are you supposed to do?
So you can add 3 always. The problem with the square root of y minus 5 is whether y minus 5 is positive. And then if y minus 5 is positive, it's the same as y greater than 5.
So the plus 3 doesn't really matter.
No. Other questions? Alright, so let me give you a function which is even more interesting. So let's have a function like this. F of x is absolute value of x if x is between 2 and minus y, minus 1, and let's say 5 otherwise. Let's talk about both the domain and the range of this function. What is the domain of this function? What numbers I can plug in to this function? Can you say louder?
For X or for Y?
So first question is about the domain. What I can plug as x? 0 to 2 and infinity. So you're probably talking already about the range, about the value of this. The first question is about what numbers I can plug into this function. Yeah,
Whole numbers?
all numbers, yes. So if x is between -1 and 2, I can plug it in and use this formula. If I use any other number, which is not in this range, well, I'll use this formula. So the domain is all numbers. Well, for the range, it's a little bit more interesting. So let's sketch the graph of this function. Graph. I have two distinct definitions of this function depending on whether x is between -1 and 2 or if it's outside of this interval. So let's see. From -1 to 2, I should just graph the function absolute value of x. I know how it looks like. It's exactly like x when x is positive. It's exactly like -x when x is negative. So I get such a graph. If x is outside of this interval, my function is just 5. So the graph is a horizontal line. The y value does not depend on x. So here somewhere I have 5, and I'll have such a graph. So this value 5 is not obtained when x is equal to -1, x equal to 2. That's why I draw a small circle. So here when x is -1, I go to this line, not that line. That's why on this line I put a circle. But otherwise, when x is smaller than -1 or greater than 2, my y value is 5. So now what is the range? What is the set of all possible outputs? What possible values of y can I obtain? Yes. So the output is these numbers from 0 to whatever this thing is, and it is 2, which is absolute value of 2. So numbers from 0 to 1 I can obtain in 2 different ways. From 1 to 2 I can get in only one way. And number 5 I can get in infinitely many ways. But the range itself is just the collection of these numbers. It doesn't matter how many times I can obtain these numbers. So the range would be x between 0 and 2, and x is equal to 5.
Is it X or Y?
Oh, sorry, 1, yes. So all y values between 0 and 2, and also the y value 5. Or if you want the interval notation, you might actually have never seen how to write this in interval notation. You can write it like this. The interval from 0 to 2, including 0 and including 2, you can obtain both these values. And also, that's how we write and also. And then there is just one single number 5, which you can write like this. In curly brackets, it means just the set of one number, just 5. But if in doubt, if you don't know how to write it in a notation that you think is smart or the proper way, write it in words. It's better to write the correct statement than to write it using proper symbols. Okay, so questions about this one? Alright, so we won't have any more complicated functions than this. This is probably as complicated as it can get. I mean, for exercises about range. So let's move on to three different kinds of exercise. True-false exercises. So for a true-false exercise, the instruction is going to be somewhat like this. Decide whether the following statement is true or false. If it is true, prove it, or explain it, or justify it. If it is false, provide a counterexample. So decide whether the statement false. If it is true, explain why. Prove or justify why. If it is false, provide the counterexample. And then you have some statements. So let me give you some statements. Let's say let's start with something simple. If a line intersects, and if a line in a circle intersect, then we intersect at least two. So here's a statement. It reads, if a line intersects a circle, or if a line and a circle intersect, then they intersect at least at 2 points. So let's decide, is it true or is it false? Let's vote. Who thinks it's true? Okay. Who thinks it's false? Okay. So let's start with the true opinions. So what would be the reasoning to explain why it's true?
I think a tangent doesn't count as an intersect, so if it goes through mass, it goes through 2 points.
So say it again.
Saying, like, someone who says false may say tangent is intersecting, but tangent's only touching it.
Ah, I see, interesting.
That's my,
Okay. So apparently all of you got the kind of the borderline case of, so of course there are circles and lines which intersect at 2 points. Like take any circle, take more or less any line which intersects it, you will get intersection at 2 points. But if the statement is about every possible line and every possible circle which intersect, you should also think about borderline cases. And in this case, will be you got the right borderline case, which is a tangent. And well, when we talk about intersection, we talk about just intersection is whenever the 2 figures have at least 1 point in common, which in this case it is true. So we do say that the circle and tangent line intersect. Probably if you kind of did have this example of tangent and you said that tangent does not intersect, just touches, you'll get half the points for this question because you understood the essence of the question but didn't quite get the right notion of what intersection means. Well, so this statement is actually false. So our answer will be like this. False because a circle and any of its tangent lines intersect at 1 point. And since the question asked for an explicit counterexample, if the statement is false, we should actually provide a counterexample. In this case, maybe even a picture is enough. So let's have a circle and a tangent. So that would be a counterexample. Some case of a circle and a line which intersect, but only 1 point.
so we don't have to provide like an equation or anything?
It might be even better if you provide an equation. Let's say a circle would be x squared plus y squared is equal to 1, and the tangent line would be y equal to -1. So these 2 things intersect at 1 point, which is 0, -1. It would be even better if you provide the picture and also explain what this picture means. Like in this case, we did explain what this picture means. It's a circle and one of its tangents. So it's also enough. It's like if the question was about a function and you want to justify something about the function and you just provide the graph of this function, not an algebraic formula, it's enough if you explain in words what kind of features this graph has. So let's say the graph is always increasing and you draw some line which is always increasing, then it's enough. So how would you justify this? So the question was, isn't this statement true because we we do have examples of a circle and a line which do intersect at 2 points. Well, the statement itself is, the way to read the statement is, so the statement is if a line and a circle intersect, then some. It means that you should think about any possible line and any possible circle which intersect. And it's not enough to consider just examples of circles and lines which intersect at 2 points, like this one. You have to justify why the statement would be, if you were to try to prove that it's true, you would have to justify why it's true for any line and any circle which intersects at least at 1 point. But you do have a line and a circle which intersect only at 1 point. The statement is false. Okay, other questions? Yeah. Oh. Well, a line is a line. A line is infinite line, and a circle is the whole circle.
Okay.
So if it talks about a line and a circle, you should take the whole of the line and the whole of the circle. Just to repeat the equation was, is it possible that you kind of have a line and a circle which intersect at 2 points, but somehow you restrict the domain and the range to include only this 1 point? And that would be a bad example because the question asks just about a line and a circle, not about a line and a circle in a given domain in a given range. So you have to take the whole line and the whole circle. So this would not be a counter example. Okay, so let's move on to a different one. Let's say like this. If f plus g is continuous, then f is continuous and g is continuous. Second exercise. So this statement is like this. If sum of 2 functions is continuous, then each one of these functions is continuous. Let's start thinking whether it's true or false. Any ideas? Yeah.
Is it false?
Why do you think it's false?
Because either your function of x or your function of g could, like if your function of x was just the absolute values of x, so it won't be satisfied for positive x values, then the function wouldn't be continuous, I guess. Because then if g, unless g satisfies all negative values, then the function wouldn't be continuous, I guess.
I'm not sure that I really understood your example. So I understand that you're trying in your mind to construct an example of something which would be continuous for positive numbers, maybe continuous for negative numbers, but maybe a total zero. Is that what you're trying to do? Okay. So first idea would be, this question asks about continuity. If I were to construct a counterexample, well, how can I construct something which is not continuous? Well, one possible example would be identifying a function by cases, maybe something for x positive, something for x negative, and the two things wouldn't match at 0. Okay, maybe a good idea. And then How will you continue from here?
Well, then you would have to show that the limit does not exist. If the limit does not exist, then the function is not continuous.
Okay. So maybe let's take f to be one of these discontinuous functions. Actually, a function which has a problem at 0.
Okay.
Now I still want to have a g such that f plus g will be continuous. How can I achieve this? So we are starting to construct another example. Starting to construct a counter example. We might succeed, we might not succeed. So that's the nature of these questions. If you decide that you are going in one of the two paths, either prove that the statement is true or decide that it's not true and try to construct a counterexample, you might succeed or might not succeed. Regardless, you will understand something about this question. So the suggestion was, well, I want a counterexample to this question, which means I should find f and g such that f plus g is continuous, but at least one of f and g is not continuous. So let's start with an example of a function which is not continuous. Something like this. Let's say like this. So let me start with f which is not continuous, something like this. Now I want to find a g, an extra function g, which I don't care whether it's continuous or not continuous. My f is already discontinuous. But such that f plus g is continuous. Can I find such a function? So let me write this now. We want to come up with g such that f plus g is continuous. So at this point, if you manage to come up with such a g, then we are done. We construct a counterexample. If we, for some reason, try and never come up with a g, then maybe it's some evidence that the statement is actually true. Because at this point, we have no idea whether it's true or false. So let's try. How can we make it the sum of f and g actually continuous? Or
Say f for all values set x is less than 0 equals -1. And for g for all values greater than or equal to 0 equals 1.
but then you won't be able to take the sum of these functions. Because to find the sum of the functions, you have to plug in numbers for which both f and g are defined. If there are no numbers for which both are defined, then there is no sum. So you do want to take a function which is two functions with the same domain, and then their sum will be defined on the same domain. So, other ideas?
Would you be able to like do like basically the opposite of that function, like for where y is lower than 0, you just for the g function, you do it like y is greater than 0, and then when y is greater than 0, you do it y is less than 0, so then it kind of like
Okay,
like that?
yes. So the idea is like this. This function is discontinuous because of a jump of height 2. Let's balance it out by adding a function whose jump will be minus 2. And then the sum will have no jump whatsoever. So let's take g, give something like this. So this will be a staircase like it was here, but in the opposite direction. And then the hope is that f plus g would be actually, well, what is it going to be? Well, x is positive. I will add 1 and minus 1. 1 plus minus 1, which will be 0. When x is negative, I'll get minus 1 plus 1, which will be 0. And when x is 0, I'll get minus 1 plus 1, still 0. So this function is actually continuous, always 0. So we did manage to construct a counterexample. Let's write down this counterexample. F of x will be 1 if x is greater than 0, and minus 1 when x is smaller than 0. G of x is going to be the opposite, minus 1 when x is positive, and 1 when x is negative. And then f plus g is always equal to 0 for any value of x, regardless whether it's positive or negative. Okay, fantastic. Can anyone come up with a different counterexample? Or maybe a whole family of counterexamples? Something which is built on the same idea. Will you say it again? I wasn't here. Okay, so what's the idea here? We've taken a function f, which was discontinuous. Let's for now forget about the actual formula for this function. It was some function. How given such a function f can define a corresponding function g? Such that f plus g will be continuous. In fact, such that f plus g will be 0. Negative f, yes. So here's a whole family of examples. Take any f, just any, whatever discontinuous function you have in mind. Maybe the Dirichlet function from your tutorials, or I don't know, your favorite discontinuous function, some staircase like this. Take as g, just minus f. The sum is going to be continuous always, because it's always 0. Okay, so questions about this exercise? Just a small warning. If the statement was in the opposite direction, if the statement was something like this, if f is continuous and g is continuous, then the sum is continuous, then the statement would have been true. We know that sum of two continuous functions is continuous. So one kind of easy way for us to construct these true-false statements would be to take something true, change it a little bit, maybe change the order of the statements in the actual statement, and ask you whether it's true or false. Well, here's a way for you to come up with examples on your own. Take any correct statement from our class, for example, the intermediate value theorem. If the function is continuous on the interval and it has different values of different sign at the endpoints, then it has a 0 in between. Mess it up a little bit. For example, if the function has a 0 on an interval and is continuous, then it has different signs at different endpoints, and try to think whether it's true or not. Just if you want more exercises, try to do it with each of the two statements we have in class. You'll usually get false statements, and as an exercise, come up with counter examples. Okay, let's let's have something else. Let's say if let's actually solve something about the intermediate value here. So if f is continuous on 0, 1, and f of 0 times g of 1 times f of 1 is smaller than 0, then f of x is equal to 0 for some x between 1 and 0. This statement definitely looks like something related to intermediate value theory. Except, of course, it might be false and then it's not related to anything. Or maybe it's true and then it's probably related to intermediate value theory. So any ideas? Is it true? Is it false?
It's true because there's a sign change between 0 and 1, and so therefore it must cross the x-axis between point 0 and point 1. And
Okay,
so,
why is there a sign change from 0 to 1?
because, well, we know f of 0 is 1, or when x is 0, the y value is 1, and so you know,
Why is it?
because f is continuous on 0 or 1.
There are many continuous functions from 0 to 1. Like such a function is also continuous. This is 5. Yeah.
It's false because it crossed between 1 and a half. If we go back to the axis, we cross the axis more than once. So there, for
And
example, let's do
even
it.
initial boundary example.
Okay, let's say f of 0, f of 1 equals a positive number, because it goes to negative.
Okay, I should give a counter. If I want to give a counter example, I would have to give a counter example with product smaller than 0.
Yeah, so you can put f of 0 and f of 1 are both negative. Okay.
And that's not part of the conclusion, it's part of the condition. So my condition is my function is continuous and the product is negative. And then the conclusion is that the function is 0 somewhere in between. So if you want to provide a counter example, you should come up with a function which is continuous, for which this product is negative, and which is not which does not have a 0 in between. So if you come up with an example which is continuous and the product is positive, it's not a function. Yeah.
If f 0 and 1 less than 1, we know that 1 and 2 value is negative,
Mhm.
which means that at some point,
What about the other one?
right,
So you said one of them must be negative. What about the other one?
the other one must be positive.
The other one must be
Both
positive.
of them are negative,
Okay.
must be positive.
So we have a correct proof here. This statement is actually true, and the reason is, let me just say the word for just 1 minute. The product of f of 0 and f of 1 is negative. What does it mean? How can a product of two numbers be negative? Only one of them is negative and the other one is positive. They cannot be both positive or both negative. So f of 0 times f of 1 being negative means that exactly that one of f of 0 and f of 1 is negative. The other one f of 0 and f of 1 have different signs, we have no idea which one is positive, which one is negative, but one of them must be positive, the other one must be negative, in order for the product to be negative. And then, by intermediate value theorem, well, the statement is true. There is x between 1 and 0 such that x is equal to 0. Because f is continuous and the values at the endpoints are different. Alright, so have the best luck today. Good evening. We'll see you with